Welcome to qnawire.
For problem 124, we're asked to find the center of gravity of a paraboloid of revolution by integration, direct integration. And we're asked to find the center of gravity of two components where it's split halfway along the x-axis like this. And if we take the entire distance along the x-axis of this paraboloid as h, both of these would be h over 2. Both sides of the components, component 1, component 2. And to find the center of gravity, or a centroid, we'll integrate over a bunch of small disks, like so, to find the centroid in this equation, where the centroid times the volume of each component is equal to the integral of that differential element, the disk, dv. And so let's start with component 1. We'll need the volume on that left side of the equation. And the volume is going to be equal to the integral dv, where the dv, the change in volume of that differential element, the disk, is going to be pi r squared, so a circle times the change in the x direction to give us the small differential disk. Now the equation of this paraboloid is equal to x is equal to h minus h over a squared y squared. And since we know that, we can substitute out r, because we don't know the radius, but in this problem we're allowed to use the height as something that's known, the height of the paraboloid. And plugging in r for y, because the radius is along the y-axis, see that r squared is equal to a squared over h times h minus x. And so now we have, plugging that back into dv for the radius squared, we have that it's equal to pi times a squared over h times h minus x dx. Now we can solve for the volume of component 1, integrating from 0 to h over 2, because component 1 just goes to half the height of the paraboloid. We can plug in dv, and the a will cancel, so we'll just be left with h. And a in a paraboloid is its radius, I believe it's called the minor radius, the smaller one, shown in the diagram I just drew. In solving this integral, we get pi a squared over h times x minus x squared over 2 from 0 to h over 2. This simplifies further to 3/8 pi a squared times the height. And now we need to find the right side of the equation, which is the integral of the differential element dv. And so again, we'll be integrating from 0 to h over 2. And we can plug in x for this differential, the centroid element, differential element centroid, because the it'll continually move along with the disk at whatever value of x until from 0 to h over 2. So we can just plug in x for that, and then we can plug in dv, which we solved for just a moment ago. Solving this integral, get that it's equal to pi a squared over h times h x squared over 2 minus x cubed over 3 from 0 to h over 2. And this simplifies to 1/12 pi a squared h squared. And now we know everything we need to find the centroid. So we can plug in that the centroid of component 1 times its volume we found (3/8 pi a squared h) is equal to the right side of the equation, insert the integral of the differential element, 1/12 pi a squared h squared. Solving this, we get that the centroid of component 1 is equal to 2/9 the height of the paraboloid. Now we can use the same method to find the component, the second component. This time for the volume, we're integrating from h over 2 to the complete height of the paraboloid. And the differential element of volume is going to be the same because we're still integrating a disk through. So we just plug in dv from before. Solving the integral, we get pi a squared over h times hx minus 8x squared over 2 from h over 2 to h, which simplifies to be pi over 8 a squared h. Now we need to solve for the right side of our centroid equation, which is the integral of the differential element dv. Integrating from h over 2 to h again. And just like the first component, we can plug in x for the differential element, and then we know dv as well. This simplifies, or solving the integral, it becomes pi a squared over h times an h x squared over 2 minus x cubed over 3 from h over 2 to h. Simplifying further, we get the right side of this equation is going to be 1/12 pi a squared h squared. And now we can plug this back into our original equation for the centroid of component 2. We plug in the volume we found, pi over 8a squared h, and set equal to the integral of the differential element, 1/12 pi a squared h squared. We get the centroid of